All right, welcome back, young students of chemistry. I'm going to do a couple of example calculations with you, the type of heat calculations that you might see in your first year chemistry class. Remember that in the last recording you learned that we can solve for heat by using the formula Q equals mass, Q being heat, times specific heat capacity, times the change in temperature. And this is if there's only one substance and it is not going through a phase change. So not changing state. And then you learned that we can look at heat transfer to determine what a substance is doing. So if you have two substances where heat is being transferred, you're going to use mc delta T, that's heat, of the system, and you can define your own system, is equal to the quantitative heat of the surroundings. So we can measure what's happening to the surroundings, and we can apply that to the system. Now remember, the key words here is if we have two substances, and if you see the word in a calorimeter. And then you have heat of phase change. So if a substance is melting, we will use the enthalpy of fusion expressed in kilojoules per gram. Sometimes that's expressed in kilojoules per mole, but well, we're going to use grams. Sometimes we'll use moles. So enthalpy of vaporization for boiling and condensing, that's going to give us some amount of heat, again in kilojoules per gram or kilojoules per mole. So this is how we're going to solve these problems when these substances are changing physical state. So keep that in mind as we go through these, and let's get started. Pause the recording when need be. So here we have a problem. How much heat is needed to raise the temperature of 600 grams of aluminum from 25 to 300 degrees Celsius? So a couple of things you need to consider about this problem is, will the aluminum melt? You know, we're going from 25 to 300, and this is the melting portion of the curve. 25 degrees would be down here. You know, so do you think that 300 is going to be up here somewhere, or is 300 going to be down here? And that really depends on the substance. So what you're going to want to do is look up the temperature of melting for that substance if you don't know it. We know that aluminum is a metal, so it melts at a high temperature. As a matter of fact, it melts at something like 600 degrees Celsius. So again, by looking at that, we know that the aluminum is not going to melt. So we should consider as heat transferring. And that means that we would have two substances. Since we only have one substance that we're dealing with here about the aluminum, then we do not need to consider heat transfer. You would see the words in a calorimeter, or you would see more than one substance, typically the substance that you're interested in, and the surroundings would be water. So we know that we can use, because we have a mass and we have a initial temperature and we have a final temperature, we know that we can solve for heat by using Q equals mc delta T. Heat is equal to mass times the specific heat capacity for the substance, aluminum, times the change in temperature. So 600 degrees Celsius, or 600 grams, is our mass. The specific heat capacity for aluminum is something you can look up. I happen to know that it is 0.900 joules per gram degree Celsius. There's charts of these in your book, or you can ask Siri or Google or whoever it is you like to talk to on your phone. And then final temperature minus initial temperature, 300 minus 25 is 275.0 degrees Celsius. And then from this point, it's just chugging it out in your calculator to get the heat. You'll notice that units that cancel are, let's see, there's a gram on top and a gram on bottom, a degree Celsius on top and one on bottom, so those cancel. And we end up with 3 significant digits, 149,000 joules of heat. If you're uncomfortable with that big number, why not just plunk it into kilojoules by moving the decimal 3 places to the left? So that would be 149, kilojoules. The easiest of the heat problems. Okay, the second one here is we have to ask ourselves, hey, read the problem. Will it go through a phase change, or are we dealing with heat transfer? And here we have a metal, and we also have water. So because we have 2 substances, we're dealing with heat transfer. So we know that we're going to use the equation mc delta T of our system, in this case the metal, is equal to the opposite heat, mc delta T, of the water. So what are we solving for? It says, what is the specific heat of the metal? So we're solving for the specific heat capacity of our metal specifically. Algebraically, specific heat capacity of the metal equals mc delta T of the water over m delta T of the metal. And now again, we can plug and chug. The mass of the water, since we know the volume of the water is 100 milliliters, and we know the density, the normal density of water is 1 gram per milliliter, we can say that that's 100 grams of water. The specific heat capacity of water, we can look that up in a reference book, 4.18 joules per gram degree Celsius. And then the change in temperature of the water. So the initial temperature of the water was 34. The final temperature of the water was 36. Subtracting and keeping that decimal place, we have 2.0 degrees Celsius. Looks like our thermometer is going to determine our significant figures on our calculation. And then on the bottom, the mass of the metal, that's 50 grams. And the change in temperature of the metal, it says the initial temperature of the metal was 95. We know that the heat will stop flowing when the temperature and the water are the temperature of the water and the metal are the same. So we'll do 95 minus 36. The heat of the metal went down and it went into the water. So we can just solve this, chugging it out in the calculator. To 2 significant digits, because of our thermometer, the specific heat capacity of the metal is 0.28, and the unit is, let's look at the units that cancel. Grams cancel, degrees Celsius cancel. None of this unit cancels, so that's our unit, 0.28 joules per gram degree Celsius. And we could look at a list of specific heat capacities and determine what the metal is made of. Okay, last one. So in this example, we're solving for how many moles of water at 100 degrees Celsius and 101.3 kPa, kilopascals, can be vaporized by the addition of 180 kilojoules of heat. So one thing you notice about this is that this is standard pressure, and this is the normal boiling point of water. So we don't need those numbers, but they're just telling us, hey, there's nothing weird going on here. The water's boiling at 100 under standard conditions. So we know that if we have 180 kilojoules of heat, we know that we can use the enthalpy of vaporization for water, which is 2,260 joules for every gram of water that vaporizes. That's one of those constants. You do not have to memorize it, but I gave that to you in the first presentation. Now notice what we have here. We cannot cancel our kilojoules, can we? Because our enthalpy of vaporization is in joules. So we need to convert our kilojoules to joules, and we will do that by adding 3 zeros there. And now we've got joules. And it says how many moles of water. So what we have here is grams of water. And of course we know ye old molar mass of water is 18.02 grams for every mole. And then we can chug it out in the calculator. Be sure to put the things in the bottoms in parentheses when you divide. Otherwise you're not going to get the correct answer. Oh, I forgot to put it into joules. And that is 4 we've got two significant digits, 4.4 moles of water. Okay, I hope that helps out. And that is it on the types of calculations for heat. It doesn't include the more complicated ones where they're going through several different changes where, you know, it's increasing its temperature to the melting point and then increasing its temperature and then adding heat and melting and then increasing the temperature more and adding those heats together. We've gone over some of those in class, so or several of those in class, so I think we're probably okay on that. If you need another recording on that, you'll need to let me know. Okay, thanks.